Section. Introduction. We're going to talk about how language changes over time and how this can affect the performance of language models. This is known as temporal misalignment, where the training and testing data don't match up in terms of time periods. This can cause a significant drop in performance. To address this, we need to adapt our models to work well with data from specific time periods. However, this is a challenging task due to the many different timescales and the possibility that we might not have data from the target time period. Recent studies have shown that we can modify the behavior of neural networks by interpolating between the parameters of fine-tuned models. We're going to show you how this method can be used to adjust language model behavior over time in a cost-effective way. We'll introduce something called time vectors, which are an extension of task vectors. We fine-tune a pre-trained language model using text from a single time period, then subtract the pre-trained weights. This gives us a vector that represents a direction in weight space that improves performance on text from the target time period. We'll analyze the structure of these time vectors using datasets organized by time for language modeling, classification, and summarization. Our findings suggest that time vectors are intuitively organized on a manifold. This means that time periods that are close together yield time vectors that are also close together in weight space. We also found that temporal degradation in yearly and monthly settings is strongly correlated with the angles between time vectors. We use this structure of time vectors to create models that perform better on data from new time periods. By interpolating between two time vectors, we can find vectors that improve performance on intervening months or years when applied to the pre-trained model. This structure can also be used to generalize task-specific models across time periods with similar time vectors specialized to unlabeled data. Our results show that temporal variation is somewhat encoded in the weight space of fine-tuned models, and that weight interpolation can help customize language models to new time periods. We're making our code, data, and over 500 models fine-tuned on specific time periods publicly available. In the next section, we'll describe our datasets and fine-tuning techniques, which form the basis for all our experiments. We fine-tune language models on multiple time-stratified datasets, which we use to analyze temporal misalignment and build time vectors. Then, we'll explore different ways of interpolating between time vectors to generalize to new times. We've created two new time-specific language modeling datasets from unlabeled text in news and Twitter domains. For these datasets, we measure the perplexity of the model on the test set. We've sampled articles and tweets from different years and months, and we've also measured the overlap between yearly train and test splits in both tasks using a Bloom filter. We found that less than 2% and 0.1% of examples in the Twitter and WMTLM test sets, respectively, contain contaminated n-grams. For downstream tasks, we use the newsSum and polyaf tasks. We measure each model's performance on the test set in Rouge L for newsSum and macro F1 for polyaf. To compare the same weight space across tasks, we use pre-trained T5 checkpoints for all our experiments. We fine-tune T5 small, T5 large, and T5 to 3B on each of our time-stratified datasets. For language modeling, we use the LM adaptation objective. To reduce the computational burden, we fine-tune T5 large and T5 3B with low-rank adaptation and default hyperparameters. When creating time vectors, we merge LoRa weights back into the base model before subtracting the pre-trained model. We use a batch size of 2 with 8 gradient accumulation steps. We fine-tune for a single epoch on LM splits and 3 epochs on downstream task splits. Our learning rates across all tasks are 0.0008 for T5 small and T5 large, and 0.0002 for T5 3B. We fine-tuned models concurrently with a single GPU each. We used 82080T, 4 Titan, and 8A40 GPS. In experiments for sections, we ran evaluations in parallel using available Titan, A40, and A100 GPS. Section summary. Temporal variation in language models can lead to performance degradation across different time periods. To address this, the authors propose using weight space interpolation to edit language model behavior over time. They introduce time vectors, which represent directions of movement in weight space that improve performance on text from specific time periods, and demonstrate that these time vectors are organized on a manifold. Section. Revealing temporal misalignment at multiple timescales. We're going to delve into the issue of temporal misalignment, which refers to how models' performance can degrade over time. We'll be using a new set of models and tasks for this analysis. This will lay the groundwork for our development of time vectors. First, let's talk about yearly degradation. Previous studies have shown that models' performance tends to decline on a yearly basis. To verify this, we fine-tuned different versions of the T5 model on each yearly split from every dataset. We then tested these models on different time splits of the test data. We used heat maps to visualize the yearly temporal misalignment and calculated the percent change in perplexity from the average for each year to account for inherent yearly performance differences. As expected, we saw a linear pattern of degradation in each task for all model sizes. Some tasks, like political affiliation classification, showed more noticeable degradation than others. Next, we looked at monthly degradation. To our knowledge, this is an unexplored area. We trained the T5 small model on each monthly split of the WMT language modeling dataset from 2012 to 2016, resulting in 58-month fine-tuned models. We then tested each of these models on each monthly test split, totaling 3,364 evaluations. Interestingly, we found nonlinear patterns in temporal misalignment, which corresponded to the cycle of months in each year. This pattern was evident in the stripes that appeared parallel to the diagonal every 12 months, indicating that a model trained on a particular month tends to perform better on the same month in other years. In summary, we found that while performance decays linearly on a yearly scale, there are seasonal trends in month-to-month misalignment. We then analyzed how these phenomena relate to the weights of time-specific models, and used that relationship to develop techniques for adapting language models to new times. Now, let's talk about temporal adaptation with time vectors. We used the collection of year and month fine-tuned models to study temporal misalignment through the lens of model weights. We formed time vectors by taking the difference between a model fine-tuned on a specific time and the pre-trained model. We found that the weights of two time vectors become less similar as the times they were fine-tuned on become more misaligned. We then tried to use this relationship to update models to unseen times by interpolating time vectors. To give you some background, task vectors are the difference between the weights of a pre-trained model and the same model after fine-tuning on a task. Time vectors are an extension of task vectors to the time domain. We call time vectors from models fine-tuned on individual years and months, year vectors, and month vectors. We visualized time vectors and found that time vectors closer together in weight space are also closer together in time. We measured the cosine similarity between model weights from each pair of time vectors trained on different time periods. We found that this similarity metric and performance decay similarly over time. The correlation between cosine similarity and relative performance change on different years was highest in WMT language modeling. This relationship also extends to the monthly scale. These results suggest that time vectors are organized in a way that predicts their performance on corresponding time periods. Next, we'll explore how we can use this structure to improve performance on new time periods by interpolating between time vectors. Section Summary. In this section, the authors analyze temporal misalignment at different timescales and across various domains and tasks. They find that performance degradation follows a linear pattern on a yearly scale, while month-to-month misalignment exhibits seasonal trends. They also introduce the concept of time vectors, which capture the differences between model weights at different times, and show that the similarity of time vectors correlates with temporal degradation. This relationship allows for the interpolation of time vectors to adapt language models to new time periods. Section. Generalizing to intervening time periods. We're going to discuss how to handle gaps in datasets, which can occur due to archiving issues or a low sampling rate. These gaps can cause problems for our models, as they might not perform as well during these gap times. However, we found a way to improve this by interpolating between models that have been fine-tuned on the oldest and newest times. To explain this method, let's consider two time vectors, which we'll call tau_j and tau_k. We calculate their interpolation by multiplying tau_j by a factor alpha and tau_k by 1 alpha, where alpha is a value between 0 and 1. We then apply this interpolation between the time vector of the earliest year, tau_0, and the latest year, tau_n. and evaluated at different times for each alpha value ranging from 0.1 to 1.0. Our results show that this interpolation method improves performance on the years in between the start and end years. The improvement is usually greatest in the middle years and decreases on years closer to the start and end times. The degree of improvement also varies depending on the setting, with less change in performance near alpha values of 1.0 and 0.0 in some tasks compared to others. We've also found that this interpolation method can help to improve performance on a monthly scale. For example, we can interpolate between time vectors fine-tuned on January and December of a year to improve performance on the months in between. The best interpolations for each month follow a logical pattern, with a higher percentage of the January model leading to better performance on earlier months and vice versa. Next, we'll discuss how to update models that have been fine-tuned on a source time period to a target time period using only unlabeled data from the source time period. This is useful because creating labeled datasets can be time-consuming and expensive, and language models that rely on supervision for fine-tuning can quickly become outdated. To do this, we use language models with weights that have been fine-tuned on unlabeled text from the source and target times, and a task-specific model with weights that have been fine-tuned on labeled data from the source time. We then perform arithmetic on these vectors and evaluate our estimated weights on each target time, sweeping over all combinations of 3 alpha values and reporting the best result compared to the original model. Our results show that this method improves performance on future years in both tasks. The improvement increases as the target and start years become more misaligned. The size of the model also affects performance, with larger models showing greater improvements. Finally, we'll discuss how to build models that perform well on multiple time periods by interpolating between all time vectors for a task. We do this using the model soup technique, which allows us to train time-specific models independently and combine them at any time. This method also allows us to easily incorporate new time periods by simply adding more fine-tuned models to the soup. We've created 2 types of soup: a uniform soup that applies a uniform weight among all models in the interpolation, and a greedy soup that only includes models that improve performance. We've found that both types of soup can help to build models that generalize to multiple time periods, and we compare their performance to 2 baselines: a model trained on all available data at once, and the best performing model fine-tuned on only a single year of data. Section Summary. In this section, the authors propose a method to generalize to intervening time periods by interpolating between models fine-tuned on the oldest and newest times. They show that this interpolation improves performance on intervening years in language modeling and political sentiment analysis tasks. Additionally, they present a technique for updating task models to future time periods using task analogies, which also leads to improved performance. Finally, they explore the idea of creating models that perform well on multiple time periods by combining time-specific models in a model soup, which shows promising results. Section. Results. Our findings show that models trained on a mix of data from different time periods, which we refer to as time soups, generally perform worse than models that are fine-tuned using all available data in a shuffled manner. For the WMT language model and NewsSum, the performance of the model trained on a uniform mix of data from different years is even worse than the best model trained on data from a single year, despite having access to 5 times more data for fine-tuning. The model trained on a selectively chosen mix of data from different years, which we call the greedy time soup, only shows a slight improvement over the best single-year model in the case of POLI-AF, with a gain of just 1 point in the macro F1 score. These results suggest that a model that can generalize across multiple time periods is not simply a combination of models trained on data from individual years. Future research could explore more sophisticated ways of combining data from different years to create better performing multi-year models. In summary, we have proposed methods for updating models to handle data from intervening, future, and multiple time periods using a technique we call time vector arithmetic. We found that performance on unseen intervening times can be improved by interpolating between 2 time vectors, both on a yearly and monthly scale. Similarly, we can improve performance on future data by using unlabeled data from the target time periods and applying time vector analogies. However, creating a multi-year model by mixing time vectors does not yield the same performance as a model fine-tuned on all time periods at once. Our results suggest that while time vector arithmetic can be a simple way to update models to handle new time periods, it does not necessarily improve the model's ability to generalize across all time periods. In recent years, the issue of temporal misalignment in language models has received increasing attention. Studies have shown the impact of temporal drift on named entity recognition using timestamp tweets, and have extended these analyses to language modeling in news and science domains. They found that increasing the size of the model does not necessarily mitigate temporal misalignment. Recent attempts to update language models to handle new time periods have used a variety of techniques, with mixed results. Some methods have shown limited improvement, while others have resulted in the model forgetting past data. Unlike these methods, our approach focuses on updating models to handle new time periods without needing data from the target time or additional fine-tuning. The phenomenon of semantic drift, or changes in the meanings of words over time, is well documented. Our work extends these analyses to the full set of parameters in a language model. Our work is heavily influenced by recent techniques for editing models directly using interpolation and task analogies. We apply these techniques to the time domain, using time vectors and time soups to create models that can handle data from multiple time periods.